We're going to talk about three-phase transformers. We're going to discuss construction of three-phase transformer banks. And we're going to be using single-phase transformers to build that three-phase transformer bank. And we're going to talk about how to wire them Y and delta. I don't know why the middle of that slide is empty. Advantage of the three-phase transformer bank. When you have a three-phase transformer bank, especially if it happens to be wired delta, if you lose or burn up a transformer, it will still produce three-phase power. You guys have read about that in transformers, I know. But one of the advantages of a delta system is that even if one blows out, it will still supply three-phase power to the line. So one of the big advantages of that, now it won't supply as much power, but it will not quit functioning completely as some other systems might. So this allows for greater maintenance and replacement options, as they say. And so delta, as we've discussed, has that advantage. And the other thing we want to know about delta and Y is how they're wired. We want to know what are the advantages and disadvantages. One of the advantages, like I said, with delta is that the power generally will stay on, right? If you go to an area where all the power is delta and one line falls off the pole, will it shut off? No, because you don't have a ground conductor in this system, a grounded conductor, so it's a ground fault, not a short. When that wire is bouncing around the ground, hitting cars and people and everything else in the neighborhood, it's not a short circuit, it's a ground fault. Everything around has resistance back to the main transformer, wherever that may be. So it's not going to shut itself off. So do you think that is as safe as having a grounded system? No, it's not. It's probably not. Let's put it that way. And so some areas will be delta supply, where they want to make sure the power stays on all the time, even though it's a little less safe. Then some areas will have a Y supply. You'll still see three lines in the air, but it's got a grounded system someplace where each pole has a grounded wire. You might see 4 wires going across the poles, okay? And so if one of those lines goes to the earth, it's going to short out because it's going to contact the grounded conductor, or a representative of the grounded conductor, the earth. It'll shut itself off. So that's probably a little safer. Now, why would a utility company want to have a delta supply? Because they're more concerned about their reputation of keeping the power on all the time than killing a couple of people or burning up a couple of cars. Hey, we've got insurance for that. Not a problem. So it's an attitude. Part of it is an attitude thing. So now let's talk about how to wire these things. Now, a Y is just like this thing on the left, where it looks like a Y. All the windings are tapped in the middle. Okay, they're tapped in the middle. Okay, and generally speaking, this middle point will be grounded, and that is your grounded Y. Okay, the one on my right here is a delta, and it looks like a triangle, right? Called a delta. Delta is a word for a triangle. Okay, and they have different characteristics. We talked about that in three-phase circuits, right? What's common in a Y? Current's common in a Y because it's like a series circuit, right? A delta is similar to a parallel circuit, and what's common in a parallel or a delta? Voltage is common. So it doesn't matter whether it's phase voltage or line voltage in a delta, they're both the same. The current in the Y is all the same in the phase of the line. Okay. We want to talk about marking the terminals, because one of the things you're going to do, if you wind up a lineman one of these days, or setting up a delta transformer bank from three-phase transformers, you'll find that you need to mark the terminals. And H is always the primary incoming power. Okay, whether it's stepping up or stepping down, the easiest way to remember it is H stands for high, because they're usually a step down, but they're not always. But H is always the incoming power. And then the terminals going out will all be marked X, just like in a single phase transformer. The output is going to be marked with an X. Okay. Now in this case, we're looking at a delta Y set of transformers, where we took 3 single phase transformers. We wired the primary side as delta and the secondary as a Y. Okay, input side 3 phase transformer, Y delta, second Y delta. Very nice. All right. And again, here we have our Y on the left, our delta on the right. But as you know, I don't like looking at that. Let's get my little marker out, and we're going to do the Y delta thing. Now we have our incoming power coming to our 3 different transformers. And we want to make the incoming one, what was it, delta? Let's go back one just for a second. We want to make the incoming one Y. I'm not sure why I picked that, but okay. We're going to make the incoming one Y. And so all we have to do is, let's say we're going to take the right side of each transformer, and we're going to tie them all together. Now they're all center tapped. They're not center tapped, they're all tapped on one side. And so we're going to bring in power, phase A, phase B, and phase C. So now we've created a Y input, right? And so we're going to have different voltages between phase and line on the input. Okay, now on the output, we want to create delta. Now remember that they're tied corner to corner to corner, right? So we know that we've got to tie this corner to that corner and this corner to that corner, right? That's fairly simple, right? And now, I've got 2 terminals F1. How is it possible I'm tying the first one to the last one? That doesn't make sense. Now that looks like a short circuit, right? Well, it sort of is, but it's not. That's our phase A, our phase B, and our phase C. So that's our output. Now we might be going to a delta or a Y load. Where's my get rid of these markings? Oh, they're just going to go away. Cool. Okay, so let's look at. Oh, we've already done this. We've wired one side delta. Oh, this is where we're going to. I'm sorry. This is where we're going to make the primary delta and the secondary Y. So let's do that now. And so again, we're going to tie, look at our drawing up here. So we're going to tie these together because we want to create a delta, right? And then we're going to have a Y output. So again, we're just going to take one side. We're going to tie them together. And we're going to ground that point. And then we're going to have phase A, phase B, and phase C. Okay, so now we've created a delta and a Y supply and a Y delta supply, right? Okay. So now we know how to make the connections, right? We've done that actually, and we've done that. Let's go down to this. Assume we have a 480 volt line supply. So now we're going to move down to doing an example. And we're going to assume we have a 480 volt line supply to a transformer bank, winding ratio of 4:1 step down, and we're going to do the connection. The primary is a delta and the secondary is a Y. So let's draw our connections for, we have delta Y, right? So we're going to tie these together again. And we're going to have a Y coming out of here, so we're going to tie these together. Okay. Now we want to look at, now I want to show you that you always want to look at what happens in the phase. And it also says we're going to have a delta load of 50 ohms. Okay, well, let's put our load in here too. Says it's a delta load, right? Whoops. I was going to make it an inductive load. That would be a bad idea. We want to keep this simple. So we're just going to make it a resistive load. All right. So we're going to have our connections come from A to here, and B to here, and C to our load over here. Now, this poses a problem because we don't know what we have down here except we have a resistance of, what was it? 50 ohms, right? Across each phase. Everybody agree with that? Now we want to look, it says in our book that you want to look, whenever you're calculating anything, you want to stay, this is my phrase for it, stay in phase. And I want you to stay in phase whenever you're doing calculations. But we don't have a voltage down here in the phase yet, do we? Okay, so let's start out here on the top. And we said that we have, I had 480 on the input, right? Okay, 480. And it's a 4-to-1 step down. Okay, so 480 is a line or a phase? Phase or a line? That's line voltage. Whenever you're told the power supply is, right? If they tell you 277, 480, that's the phase and the line. But if they just tell you the line, I mean, if they just tell you one number, that's the line voltage. Okay, so we're going to say that it's 480, meaning it's, if it's a delta supply, it's coming to our delta primary, then it's a 480, 480. It's all the same. But if it's a Y supply, then it's 277, 480. But, so occasionally you get extra information out of the fact that they didn't tell you the phase voltage. In other words, probably our line input is coming from a delta. The line, the pole line in the local area is a delta wired system. Okay? So, if we have 480 on the line, what is the phase voltage in a delta? All voltages are the same, right? So we have 480 volts across this winding because that is the phase voltage, because in delta, phase and line are all the same thing, right? For the voltage. Now we know it's a 4-to-1 step down, so what's our voltage across the secondary winding? 120 volts. And that is a phase voltage, right? Then we have a Y going out. Yes? Okay, if it's Y going out, when we go down here and look at the line, can we look at just a phase voltage? We don't have a phase voltage down here. We have a line voltage. Okay, so we have to look at the line voltage. What's our line voltage? If this is a Y and one phase is 120, that means that our phase voltage is 208, right? Exactly? Okay, so it's 208 volts across the line, right? So it's 208. If it's 208 on the line and we're looking at a delta load, what is my phase voltage? 208. It's all the same. In delta, it's all the same. So my totals over here at the load, and we happen to have a purely resistive load, thank God, just this one time, with 50 ohms. And we have a supply voltage on that phase of 208 volts. Everybody agree with that? Okay. So now we divide 208 by 50, and we'll find our phase current. Everybody agree with that? Okay, tell me my phase current. 1.1? 4.16 amps. Thank you. Okay, now, if we have a line, if we have a phase current of 4.16 amps in the phase of a delta, what is my line current? Okay, phase and line current are not the same in a delta, right? The phase is 4.16, so we're going to multiply that times the square root of 3, 1.7321, is we're going to ballpark that, or hit second function square root 3 enter, and you get a big long number. Do that now. Don't do that now. And multiply that times 208. Say again. 7.21. Now that is the current. 7.21 is my line current from my load, right? I have a line current. This is even the wrong place I've marked it to, right? It's not from there to there at all. It's from there to there. Everybody see that? It's from here to here. It's from phase A to phase B to phase C to phase A. It's the line current. But I have a Y output. Yes? Okay, in a Y, all current's the same, right? So what's my phase current? 7.21 also. Now I just found how much power that I'm putting out of this transformer. So how much power is coming into that power transformer? The same amount, right? Okay, now 7.21 times 120 gives us an amount of power, right? Yes. Multiply that. You've got 7.21 in your calculator, right? Times 120. And now, when we go back up here, is my current going to be 1/4 or 4 times? It's going to be that same amount of power divided by 480, right? So divide by 480 now. We're keeping it simple here, right? And we have, oh, so it's 1/4 the current because it's 4 times the voltage. Ah, okay. So what was it? 1.8 what? 1.801 will do. Because that is my phase current in my delta, right? The delta supply. What is the line current? If my phase current is 1.8, what's my line current? 1.8 times square root of 3. You would have thought it'd be 7.21, wouldn't you? Yeah, that would seem intuitive, but it's not true. What is it? Close enough. So my line, now what did we just do? We just established a method of analyzing everything in a 3-phase transformer bank, going down to a load, and then coming back and finding the current that's going in, right? We just analyzed this thing. And how did we do that? We went from the top where we have the supply voltage all the way to the bottom until we found the phase current, and then started bringing that back up. And you can see that it took us a couple of steps to get back to the top where we have 3.12 amps. That's a good process. Okay. Now, I think we should do one more example where here we did this is delta Y, right? Delta Y. Let's do the same exact load with a delta load still, except we're going to go Y delta in, Y in delta out, and then go down to a delta load. Everybody okay with that idea? Or should we do a 50 ohm Y load? No, that'd be doing your project in the lab. Let's not do that. Okay, so let's make this. We had a delta load. It was still 50 ohms. Except now we want to have a Y delta supply, right? So we're going to take a Y out of this top one. And we'll assume we still have our 480 delta supply from the pole coming to our transformer. So our line voltage is 480. I want to start analyzing, but I'll wait. Hang on 1 second. So now let's wire our secondary as a delta. Sorry. So we're going to wire the secondary as a delta, and this is phase A, phase B. Oop. Try that again. Okay. So again, we have different relationships. So let's look at our relationship in our transformer. We've got 480 on the phase, and this is a Y, right? Y input, delta output, delta load. So this is Y delta delta. Okay. Why? Why not? I know, terrible. So if this is 480 on a Y, what is our phase voltage? If we've got a 480 supply on our Y, our phase voltage is what? 277 volts. Right across this winding, right? Okay, so across that winding we have 277, and it's still a 4-to-1 step down, right? Same transformers, in other words, okay? Same transformers, different wiring connection, same load, okay? Now, if I've got 277, what is 1/4 of that? Or is it, if it's 4-to-1, is that the right thing? Is it 1/4 of that? So what's my voltage on the input, on the output, sorry? That's okay, that is phase. Now let's multiply that times the square root of 3, because we need to know our line voltage output, right? No, it's delta coming out. The phase is 69 also. Okay, so it's 69.25. Coming out on the line. And now we have that across the line of our delta load, and we know that the delta load phase voltage is going to be the same as the line voltage, right? So we know that our phase voltage is 69.25. Much easier to look at when it's delta delta, right? On the output, delta output, and then delta load. Okay, 69.25. And in this case, we have pure resistance, so we have 50 ohms. Okay, so 69.25 divided by 50 ohms. Okay, now this is going to be really simple because we're delta delta on the output and the load. So if that is our phase current, 1.385, and that is, right? What's our line current? It's that times 1.321, right? $2.4. We can go, oh no, what'd I do? Hmm. Okay. Real quickly, we have a Y input, right? We have delta out. Is that correct? Okay. And I've forgotten we had, okay, P, E, I, Z, and we have 50 ohms of pure resistance. And we have, what was our voltage? 69.25? What was our current in our phase? 1.385, thank you. And our line current was 2.4. Just call it 2.4. Okay, so that is also, is that our current across our winding? No, it's not. That's our phase current, and it's delta, right? So if it's phase current and that's our delta, what's our phase current? It's back to this. Nice and simple. 1.385. We already have it. Let's multiply 1.385 times 69.5, and we'll get a number of VAs, number of the amount of power, right? And let's divide that by what was our incoming voltage? 277? Right. So what is my current in my primary? 4 to 1, so divide 1.38 by 4. A little over 4. A little over 0.4. Point what? We're looking at the phase. We're looking at the phase. So we have 1/3 of 1.385 is 0.346. Is that right? Okay. So now this is a Y. So our phase current and our line current are the same. So the current in this line is going to be 0.346 amps, or 346 milliamps. So we can see that just changing the way the transformer is set up will change our input and output currents, right? Okay, I want to talk about one other thing. We talked about, actually I would rather go back to the other one, but that's okay. This will be fine. Now, what are these things right here? Polarity dots. Why is that important? Because what if this one is actually, you thought it was over there, but it's actually over here? What's going to happen over here? What happens with our output voltage? It's going to be subtractive. Okay? It's going to be subtractive. So we're going to have really odd phase voltages. And when we look at our line voltages, we're not even going to have the same line voltages from line to line to line. It's going to really mess things up, right? And we're going to look at that, not right now, but we're going to look at that, especially in the lab, because we're going to do these projects. We're going to wire these this way. And we're going to, one of our lab projects, or some of your lab projects, are to wire a 3-phase bank out of 3 individual transformers and to create a delta Y delta, a Y delta Y, a delta Y delta, and a Y delta delta, and an open delta, open delta, closed delta, delta load, or Y load, your choice. So That's not in the paperwork for the lab projects, but that's going to be added. All right. I think that's enough for now, and we're going to stop.